Jo. Dobré odpoledne, dámy a pánové. Vítám vás na dnešní již posemestrální přednášce z vědeckého semináře, která proběhne v angličtině, so now I'll switch to English. Let me welcome you again here at the Scientific Seminary of the Department of Physical Chemistry. But since we are in the exam time, it won't count as part of the exam. And for this part, we have an esteemed guest. But I will not be speaking about the guest myself because he was actually invited by someone else. And he was invited by Chemický spolek from our faculty, and Vojta Vysoglad will speak and introduce our guest.
Děkuju. I'll switch to Czech because I wasn't prepared to speak in English. Dobrý den, já vás tady vítám všechny na přednášce, která vznikla spoluprácí Chemického spolku Fyzikálního klubíku a Olomoucké pobočky České společnosti chemické. A je to speciální přednáška, ne protože bych přednášel já, ale protože tady máme vzácného hosta. Ten vzácný host absolvoval na University of Leeds ve Velké Británii. Od roku 2002 působí na Ústavu anorganické chemie Akademie věd, kde se věnuje syntézám. A pamětníci si možná vzpomenou taky na pořad ČT Port na České televizi. Takže já už nebudu zdržovat a tímto předávám slovo tady panu doktorovi Michaelu Londesboroughvi.
Tak já děkuju. Tak možná začnu česky, pak přejdu na angličtinu. Tak děkuju Vojtovi a Karlovi za pozvání a omlouvám se, že původním dátu právě této přednášce by mělo být už před pár týdnů, ale já jsem se malinko spletl můj diář a kalendář, takže děkuju že jste se mě takhle hezky přizpůsobili. Okay, today, well, you probably all recognize this picture, right? That's Charles Bridge in Prague. And if you follow the river about 15 kilometers north towards Germany, then you'll come to the beautiful little town of Rzeszów u Prahy. And v Rzeszów u Prahy is where I have my laboratory and where there is the Institute of Inorganic Chemistry. These are two of my colleagues with whom in my group, about which much of what I'm going to be talking about today is work with them. So I want to say a big thank you to Dr. Jonathan Bold and Dr. Marcel N. I'm a boron guy, which is amusingly usually I play a lot of cricket, and all my cricket colleagues say it's a boring guy. But I hope to not be too boring about boron. I could speak about many aspects of boron and boron chemistry, but I'm going to focus today on what we're concentrating at the moment, and that's boron power as a potential future innovative solution to sourcing some of the power that drives all our economies. But maybe I begin with a question for you. How many here are familiar with boron, the element, or boron chemistry? So a couple, that's pretty impressive, so a few. I'm used to nobody being familiar with boron chemistry, so I thought maybe it's best to begin with my sort of hitchhiker's guide to boron chemistry. As my main goal this afternoon is to convert you into the beauty of boron chemistry. So, all of you sitting here, including myself, the majority of our mass is oxygen, carbon, and hydrogen. These elements either predate the existence of stars or were generated within the hot cauldron of stellar nuclear synthesis in stars. So indeed, up to the element of iron, most of our elements from the periodic table can be traced to the synthesis within stars. But this is not the case with boron. boron is not made through nuclear fusion within stars. It's a product of what we call the X process. This is cosmic ray spallation. So after supernovae, where you have nebulae roaming through the universe, containing a lot of oxygen and carbon, for example, if they come into contact with very high energy cosmic rays, then these larger atoms can spallate, they can break up into smaller ones. And when they do so, we get from carbon and nitrogen and oxygen through that cosmic ray spallation, then it forms these lighter nuclei of boron isotopes. And you can see here there's two main isotopes, boron, boron 10 and boron 11. Of course, boron is the fifth element in the periodic table, which means it has 5 protons, and therefore either 5 neutrons in the boron 10 or 6 neutrons in the boron 11 nucleus. Now, this is rather rare compared to, say, other light elements like carbon or oxygen and nitrogen, which do have lesser isotopes, but usually they're available to us in a very small fraction of 1%. Whereas you can tell from the atomic mass of boron that the isotopic ratio between boron 10 and boron 11 is one in which there's about 4/5 is boron 11, and 1/5 of it, 20% of boron, is boron 10. So uniquely amongst the light elements, boron's second most populous isotope is available to us in 20%. And the boron 10 nucleus is a very interesting one because it very readily accepts another neutron to form boron 11. It's called a neutron capture. And that neutron capture, that proclivity of the boron 10 to take up a neutron, has many useful aspects for us. So you probably are aware that nuclear fission reactions of, say, nuclei of uranium, they're controlled by the absorption of neutrons using boron 10 enriched rods. And indeed, there's medicinal uses in boron nucleocapture therapy to also take use of this very interesting nuclear property. Both boron 10 and boron 11, for fans of NMR spectroscopy, earlier today I was pleasantly shown around the department, and so the fact that it's got a nuclear spin, a quadrupolar nucleus. Now, this is an interesting periodic table which shows the relative distribution of the elements on the crust of our planet. And you can see here that boron is available to us in relatively decent amounts. Certainly, the crust is dominated by carbon and oxygen, hydrogen, silicon, etc., aluminium. But boron certainly is more abundant than, let's say, lithium, which is another important element in terms of future power generation on this planet. And boron, like most of the other elements in the periodic table, we live on a planet which is has an oxidizing environment, an oxidizing atmosphere, and boron is found, as most other elements, with few exceptions such as gold, as an oxide. So boron on our planet, its journey after those, frenetic beginnings in cosmic spallation is found in decent amounts on our planet as its oxide. And however, it was my second favorite chemist of all time, Sir Humphrey Davy, an Englishman, who in 1808 was the first scientist to isolate the element of boron. So Humphrey Davy is responsible for the isolation of, I think, about 14 elements from the periodic table. And his genius was the first application of electricity to chemistry, and he developed new electrochemical techniques to essentially take dissolved salts of different varieties and separate those salts into their elemental form. And so he took borate salts, and did the same with that, and he was able to isolate boron. I'm a big fan of Humphrey Davy because not only was he a fantastic chemist, experimental chemist, but he was also a celebrity he used to have these Royal Society chemical shows which drew in the high society of London, and he was invited all over Europe indeed to give these wonderful talks and presentations regarding the delights of chemistry. Indeed, to one of these performances in London came and watched a young Michael Faraday, who later on was really the driving force behind the application of the electromagnetic motor. And indeed, Sir Humphrey Davy, when asked what was his most important discovery, he didn't say any of the elements he discovered. He said his most important discovery was Michael Faraday. So, indeed, I've been to see where Sir Humphrey Davy was born. He comes from a beautiful town in the south of England called Penzance in Cornwall. If you've never been, I can recommend it for a holiday. It's lovely. Right, so that's the discovery of elemental boron. Of course, as I said, to get there, he was using what was available to us. So to us humans on this planet, all the boron we can find is in this form. Here, the boron atoms are in pink. These are oxygen atoms. This is a typical borate, an oxide of boron. It's a tetraborate, which is the most commonly found natural source of boron on this planet. Now, the distribution of these borate salts is not equal over the planet. And that's because it's the specific geological conditions which provide a lot of borate materials. So these borate salts need to come up in volcanic methods to the surface, and they accumulate as they're highly soluble in water. They accumulate in streams and rivers, and then they accumulate in particular where these streams and rivers lead to the formation of landlocked lakes, and they don't go into the sea. And if the temperatures are warm enough, then these lakes, which are very rich in these borax salts, when you get high evaporation in the summer, then you can just come along and take up the borax salts. And famously, the majority of production on planet Earth was in California, in the Mojave deserts in California. There was the 20-mule team, which in the 19th century would dig up these borax salts and then take them to the town of Boron, and then they would then supply the whole world from there. But today, by far, indeed, here's the pie graph, about 70% of borax, of salts of borates are mined in Turkey. And that's simply because Turkey is on the where three tectonic plates meet. It's got all the right geological conditions that are necessary to provide a lot of borate salts on the surface. And regarding if we project forward to whether boron will become or can become a strategically important material in terms of power generation, then you'll be pleased to know that the most recent studies suggest that the availability of these borate salts, and also most importantly, the supply lines throughout the world are well established and are also very safe. Even if I compare them today, at the moment, we're struggling very much with the complexities of the distribution of hydrocarbons as a power source. So in terms of borates, if they would become an important power source, then I wouldn't expect such complications. So that's a rather handy sign. The first sort of documented use of these borax salts of course, at the time, the ancient Egyptians didn't know that they were made from boron and oxygen, but they did call it borax. It was a form of natron, as they called it. So they had the ancient Egyptians quickly realized that in their sacred tradition of mummification, that they had to desiccate, dry the body as soon as possible. And they would use often, well, originally they would use hot sands from the deserts, but then they realized that salts, and they used to call a mixture of various calcium sulfate and sodium chloride, sodium bicarbonate, natural salts that they had in Egypt, they would use for this desiccation process at the beginning of mummification. But then somebody somewhere, one of the priests, got some of this natron from the north, which is now in Turkey, and they found that this particular mix of salts performed the task a lot better. And they didn't know why, but the reason why is because it had the borax salts in, these borates, which have also, later we've discovered that they have also antimicrobial properties, as well as being very efficient at the desiccation, the removal of water. So the ancient Egyptians indeed would go on military campaigns to today's Turkey to secure access to these borate salts for their mummification processes. Maybe 1,500 years later, probably somewhere in Syria, which was under the control of the Romans at the time, somebody discovered that if you used a bit of these borax-rich salts as a flux for the melting of silicon oxide in the formation of glass, that they were able to produce glass at different temperatures, and the resultant glass, which would be doped with a little bit of boron, they didn't know at the time, had much better properties. It was resistant to rapid changes in temperature and became a lot less brittle. Those of you working in the laboratories will know that the glass that you use, where you can pour in boiling water and then stick it into liquid nitrogen and it probably won't break. That's a borosilicate glass. So it was the doping of a tiny amount of boron and borates in that glass mixture, which led to these very improved properties. And indeed, to today, really, that's the uses we have mainly for borate. So those who are in the business, in the economy of mining borate, mainly in Turkey, then the majority of their sales goes into glass and ceramics. Of course, with time, as I mentioned, we've realized that it does have antimicrobial and antibacterial properties. It's used in soaps and detergents, and you need a little bit of boron in the soil to make sure you have lush, fresh, and nice-looking and juicy fruits. So it's an important part of agriculture as well. However, where I work, my insertion into the story is in this fragment here, which is growing, and that's the specialized materials using boron. And I have a couple of examples here. So you might well have heard of boron nitride. Boron nitride is an extremely strong material, and it forms these cylinders, a bit like carbon nanorods. And then you probably also have heard of boron carbide, where the atoms of boron form these icosahedra with carbon atoms in these three sites here between the icosahedra. And boron carbide is, after diamond, the toughest, strongest material for purposes of the military, as armament plates, whether it be in tanks or body armor. So there's companies such as Ceradyne, based in the US, which has a multi-billion-dollar contract with many different many different militaries producing boron carbide for protective plating of armaments. Also, it's used to, coat perhaps reactors and others. So that's turned into a huge industry. But what I'm interested in is what happens when you take either very simple halides of boron or very simple hydrides of boron, like these two. This is a boron hydride or BH3 with usually the ligand there to support it. So when you take these very simple mono boron atom species, and if you heat them up, what they will do is they will form these beautiful polyhedral compounds, which the hydrides of boron are otherwise known as the boranes. And it's the boranes which I believe are the most beautiful compounds that we have artificially on this planet now. They've only been with us for a small number of years. But I think they're wonderful compounds, and I've devoted most of my life to studying and developing these compounds. I want to talk a bit about them and what I've been doing with them. So I showed you my second favorite chemist, Sir Humphrey Davy, a bit earlier. Well, my favorite chemist is Alfred Stock, this man here. He was a German chemist, and he was the first person to synthesize the boron hydrides, the boranes. Because of course, just to remind you, boron, like most elements on this planet, naturally occur as their oxides. Now, you are not an oxide of carbon, you are a hydride of carbon. And the reason why we exist, or life exists, is because we have this wonderful process of photosynthesis, which that takes an oxide of carbon and uses sunlight to fix it into a hydrocarbon. Now, there's no other natural process for any of the other elements. So it's unique that for carbon on this planet. So these boron hydrides, we have to make artificially, we have to synthesize. And so Alfred Stock was the first to make this synthesis. And he did so, you might recognize this ship, or if you look very closely at, do you know who these two are? Yeah, it's Rose and what's his name? Jack. So Rose and Jack fell in love on the Titanic just before it sank, and then of course their romance didn't last too long, and that was the year 1912, and that's the same year that Alfred Stock synthesized the first boron hydrides, the first boranes. So this planet has been exposed, or the first boranes to ever be on this planet came about just in 1912. So they're here for only just over 115 years or so. And Alfred Stock's initial inspiration, and I want to tell you this story because I noticed that many of you are probably coming to this stage where you're either thinking about going to university or in university doing a master's or bachelor's, you're considering a PhD, etc., etc. Well, Alfred Stock was the PhD student of Emil Fischer, who was a Nobel laureate, and his Nobel Prize was for essentially structural work on organic compounds. He was the first to understand, he was studying, for example, things that we knew about, for example, caffeine or theobromine, these compounds that we get from natural foods and drinks that we knew had an effect on us. And he was the first to determine their molecular structures. And in doing so, he realized that there was lots of commonalities amongst these molecules that had an effect on us, and that they were all hydrocarbons. And so then he understood and famously talked about this when he received his Nobel Prize. He said, to quote him, "And so progressively the veil behind which nature has so carefully concealed her secrets is being lifted where the carbohydrates are concerned. However, it is increasingly obvious that the one-sided study of carbon compounds cannot suffice to elucidate the nature of chemical processes in all its aspects. So he understood that we have this photosynthetic planet, which is able to produce for us these hydrocarbons. But he wondered himself, well, what about all the other elements available to us? And his PhD student, Alfred Stock, listened to this and decided to take this as an inspiration. And it was he who thought, well, can I do an artificial photosynthesis of sorts, take out the oxygen and put in hydrogen to other elements? And he chose originally silicon and boron. And of course, his work with boron led to these wonderful boron hydrides. So just a comparison, you'll probably be familiar, of course, with organic compounds and the structures they make. So the organic compounds make flat rings and chains, while the boron hydrides form these beautiful polyhedra. And the reason being is that boron is electron deficient. It means that it has the same number of bonding orbitals as carbon, but one electron less, and therefore it has to share electron density. And it shares electron density by forming these clusters that can delocalize some of its electrons and satisfy the valence conditions for stability. And the result is that these structures, these boron hydrides, are very stable and have very interesting and unique electric properties. And it's important to remind you that so often in chemistry, functionality and functionality and reactivity is often a result of structure. And therefore, the structures that boron hydrides make are incredibly important to understand. And of course, at the beginning, after the first discoveries of Alfred Stock, then you had the Englishman Christopher Longwood-Higgins, who partially solved the puzzle of Alfred Stock he didn't know what the structures were. He didn't understand that these were polyhedra. He could determine the empirical formulae of these compounds. And the empirical formulae suggested something strange. It didn't really work out into our common understanding of two-center, two-electron bonds like we see in carbon hydride chemistry. Longwood-Higgins suggested that there might be triangular networks with a delocalized electrical sharing, which enabled these three-center, two-electron bonds. Like we see in these compounds here, where you notice that even the hydrogens look divalent. They're not divalent, but they're sharing two electrons amongst two boron atoms and a proton. So eventually, William Lipscomb, he was able to categorically classify these structures using X-ray crystallography, and that work got him a Nobel Prize. Subsequently, two guys, indeed this is a photograph that I took at Leeds University, where I did my PhD. This is Ken Wade and Robert Williams, and they classified these boranes into closo, nido, arachnoboranes, and essentially they linked the structure to the electron count. Czech Republic, or Czechoslovakia then, played a huge role in developing this chemistry. So after the discovery, this is in UACh, where I've got there's a top secret, where it used to be a top secret research facility, and this is where we looked into developing these compounds, in particular as uses as rocket fuels. And there was competing projects on the American side in Project Hermes, which was led by this man here. This is Frederick Hawthorne. This is at Liblice Castle in Czech Republic, not far from UACh. And this is the first ever boron hydride international conference, IMI-Boron, which was set up by our institute. And so that thus began the Czechoslovakian impact into its chemistry. So that's a quick overview of the history. So 1912, Alfred Stock, the first boranes. Then there was this Cold War period where a lot of work went into, top secret work went into rocket fuels based on the boron hydrides. Interestingly, today, some of the rockets used by Elon Musk use some boranes in the initial thrust. You can see the giveaway green light when these fuels are being used. And after the declassification of the boron hydrides as a rocket fuel, then there came a massive expansion in the chemistry and the number of molecules that we were able to discover. And a lot of this work was coming from the group in UACh and others around the world, in Europe and America, Japan, etc. And they found that these boron hydrides can form single clusters. They can join together to form what we call macropolyhedral clusters. That was my PhD thesis, was in developing routes into the macropolyhedral clusters. They can react with other heteroatoms, such as carbon or other p-block elements, or indeed metals. And so they can, in its structures, they can incorporate all sorts of different elements from the periodic table. Since about the year 2000, since about when I began my sort of my PhD, or beginning to finish my PhD, then the focus started to shift from it being a purely sort of exploratory chemistry of discovering new molecules to trying to understand what properties these molecules had, and whether we could make use of these properties to aim towards applications. And there's been all sorts of interesting work. So I've been involved in work with microelectronics, for example, the use of these boron hydrides as dopants of boron into silicon for the fabrication of semiconductors. These boron hydrides can be used to modify metal surfaces, for example, and alter the properties with a molecular layer. These compounds can be used to selectively extract radionuclides from water. I had a fascinating talk with the gentleman at the back there about his attempts to take out various pollutants from waters, and in a similar way, you can do these with the boranes. And also, Karel will know perhaps more than I do about the potential for the use in modern medicine. So this is a diagram of the protein, the enzyme HIV protease. So HIV protease is an important enzyme for the HIV virus. It essentially cuts the genetic material once the virus has hijacked the DNA reproducing apparatus of a cell. It then has to cut it into the correct in the correct positions, and this enzyme does that job. And you can see here, blocking the enzyme active site are two molecules of a cosane borane, which is this sort of molecule. So there's all sorts of applications there as well. But what I'm going to do is I'm going to talk about my favorite molecule, and I've got two versions here. This is a present from Carol, which I'm very grateful for. This is a sort of a Van der Waals version, and then this is a sort of a classic ball and stick molecule. This is perhaps my favorite molecule. Was deeply, intimately involved in this molecule. It sort of occupies a lot of my thinking time. I'll pass it around. The green atoms are boron, the white are hydrogen. So it's B18H22. And B18H22, when you synthesize it, it forms two isomers, syn and anti. It's literally how the two subclusters are conjoined, what angles they are. I'm going to talk particularly, I was working with both these, when you make it, you get a 50-50 isomeric mixture. I was working on its application as a dopant into silicon. So the idea here was, usually when you dope boron into silicon to make a p-type semiconductor, you accelerate ions of BF3, and these can penetrate very deeply into the crystalline silicon layer, much like if you were to fire a cannon into a forest. But if you hit the surface with a B18 molecule, then the impact remains shallower. And so these produce ultra-shallow semiconducting devices, so they reduce the distance that is required to travel for the 0-1 binary code, so it makes things a lot faster. And so I was working on that for a number of years, and one day, actually, I was working on separating these two isomers, and both of which form colorless solutions. And I was pouring this colorless solution through a column, a silicon column, to separate them. And as I was doing that, it happened to be a really nice sunny day in UACh, and I noticed all of a sudden that the column was beginning to irradiate an intense blue color. And so looking deeply into that, realized that what was going on is that this molecule here, this is the anti-isomer of B18H22. The anti-isomer was fluorescing a beautiful blue color. So here is a solution of B18, and you can see if I hit it with an ultraviolet laser, it gives this wonderful blue emission. And so I began to become interested in this, in this just phenomenon. So beginning very quickly and easy, something I could do myself in my own lab, was just to measure its simple absorption and emission properties. So you can see here, this is the absorption curves. This is the absorption which leads to the emission. So it's about 355 nanometers, which is near UV, and then it gives this wonderful blue emission. And the first question I had for myself was, well, why is it that this isomer fluoresces so strongly and its other isomer not at all? So that was the question I asked myself. It took me a couple of years to actually get to the bottom of it. Here's a summary. I mean, when we started looking a bit more time-resolved spectroscopy, then you can understand something about the excited states. Because fluorescence works such that molecules occupy what we call a ground state. That's its normal energy level. And of course, in that ground state, it's going to be moving, it's going to be wobbling. And then at certain frequencies, it can absorb a photon. And when it does so, it promotes itself to an excited state, where it's beginning to move a bit more in this excited state. And then what you can do in this excited state, what can happen for most molecules when they become excited, they return to the ground state by just shaking, just movement, which turns into heat. But in the case of anti-B18, it can't do that. And in frustration, it relaxes, it goes back down to the ground state by releasing from itself a photon of blue light. Now, the excited state, we can actually work out how long the molecule remains excited for. And here's the results here. So for example, the red curve is anti-B18, and the black curve is syn-B18. So, and this is time in picoseconds. So if you look at this, if you look at the isomer that doesn't fluoresce, after excitation, it releases the energy extremely quickly, just by shaking, just by vibrations. Whereas anti-B18, once it's excited, it stays excited for a long time. 11.2 nanoseconds, which in terms of performance, that's a long time to be excited for. So even other fluorescent molecules might have lifetimes of about a nanosecond. This is 11.2 nanoseconds. Now, this is an important fact about this molecule, which I'm going to come to previously, if you remember that. So also what you can calculate is the efficiency of this luminescence, of this fluorescence. And the efficiency in terms of this molecule is an amazing 97%. Okay? So that quantum yield of fluorescence is huge. But of course, I ask myself, what about the remaining 3%? What happens to the remaining 3%? So having answered the question about the difference in the isomers and this amazing quantum yield of fluorescence, which I thought I want to develop, I also thought to myself, well, what happens in the 3% of the time? So what happens is that, of course, there exists a probability, a small probability, that the molecule, once excited, has enough energy to overcome the barrier to get to what's called the S1, S0 conical intersection point. That's this point here. That's the point at which, if the molecule has enough energy to overcome this barrier, and in the case of anti-B18, it's 0.65 electron volts, it's big, then it can get to this point here, it can relax just through vibration, right? So that's this really dodgy path to the mountaintop. It can happen, but it's very rare. Another thing that can happen is that you can get what's called intersystem crossing. This is a spin forbidden. This is forbidden in quantum mechanics, but it does happen. And that's when you get a quantum hop, from an excited singlet state to triplet state. And then subsequently, that energy can be passed on to molecular oxygen, and you'll see a phosphorescence from the excited triplet to singlet oxygen. And that's got all sorts of interesting applications, antibacterial applications, etc. I don't have time to go into that, unfortunately, but we did publish the results from this. We found that using chemistry, and this is an important principle, using chemistry, we can manipulate the photophysics. So we can manipulate the photophysics to promote certain pathways. So we could make the singlet to triplet intersystem crossing pathway more likely by adding bulky iodine groups or thiol groups onto the molecule. So we keep the same boron hydride molecule, but we do the substitution chemistry to promote these differences. Finally, what can happen is that whilst in its excited state, it can absorb another photon and become even more excited. And in these various further excited states, you can get all sorts of other different chemistries. But to conclude in this little section, what we did discover is because of its very high quantum yield, of course, this molecule works nicely, not brilliantly, but works very nicely as a laser gain material. Now, there's two essential things. If you're interested in buying a laser or a laser compound, a material that can produce laser gain, then you're interested in two things. First of all, it's efficiency, laser efficiency, and secondly, it's photostability. How long can it be used before you have to buy a new one? In terms of photostability, then this is the curve. The black one here, the black curve here is our anti-B18. It's very, very stable. This is the energy dose, and it maintains its activity on and on and on. So it's up there in terms of the market. It's right at the top for photostability. However, by the way, big thanks to Luis Cerdan, who did this work with me. Its laser efficiency is only 10.5%, which is not too bad, but the market blue laser market is usually going about 30%. So we're about a third of the efficiency. We now understand the reasons why it loses its efficiency at fluorescence is almost unity, but its laser efficiency is only 10.5%. And there's good reasons why, and it took us about 10 years to find out and work out why, but that would have to be a subject of another lecture. I'm going to move on, because time is of the essence, and I wanted to also touch on that reading this work, luckily for me, was a chap called Miroslav Krus, and he works at the Institute of Plasma Physics in Prague. And he had read some of the publications we had on the photophysics and the use of the photophysics in laser technology of this compound. And so he called me up saying, Michael, we're interested in understanding how we can push the system even further to get plasmas of these materials like what we're dealing with. So my expertise at the time was, if you can imagine the B18H22 molecule, you pump it with energy, with light energy, and the result is the electrons absorb that energy and they promote themselves to excited states. But if you keep pumping more and more energy, the intensity goes up as well, and the energy, then what happens is that essentially the electrons ionize, and you begin to start forming a plasma of boron and ions and hydrogen. And so I became part of this new European project where we're looking to study boron plasma, or borane plasma, or hydrogen and boron plasma from these molecules. And so within this project, then of course, so we're in charge of to conceive, what would be the new compounds that we're interested in making, their synthesis, then importantly, the fabrication into targets, structurally characterizing both the molecules we use and also the targets we generate, and then finally to be there when we do the laser-driven experiments at hitting these targets with very high energy light. And if we looked into the literature, what went before us, I was completely shocked at what kind of things the physicists were using as targets for boron-hydrogen fusion. I mean, they were using things like doped silicon or polymers with doped boron. It was quite strange, really, because, of course, hydrogen and boron, in hydrogen and boron fusion, well, you just need boron and hydrogen. You don't want other heteroatoms in there because they take away energy from the system. Imagine if you're using light to form these plasma, and then in that plasma you need to accelerate those ions to velocities which engender proton-boron fusion. You can take away energy from this system by simply accelerating other heteroatoms which do not participate in proton-boron fusion. So we made a lot of target molecules that we began testing. We're working with the PALS laser in Prague. The Czech Republic is blessed with several high-energy laser facilities which are of a high international standard. So we're using 30 petawatts per centimeter square of energy. So it's a 550 joule laser. This is a lot of energy, and we're smacking them into our targets. And almost immediately we got very positive results. These are the records produced for proton-boron fusion. You measure the efficiency of proton-boron fusion by looking at the alpha particles that are produced. So if you fuse a proton with a boron, it then gives off 3 alpha particles. Those alpha particles are charged. If they pass through a magnetic field, they will conduct an electrical current. And you can measure the alpha particles coming from that. And this is the number of alpha particles produced per shot. And our first experiments gave us these results here, almost as good as the top ones there. And of course, we've done a lot of work since then, but I'll be talking about that later on, or on another occasion. Very quickly, what can we do to play around with these targets? What can we change? So boron, if you remember, first of all, there's the isotopic mixture. If you remember, boron 10, boron 11. So for boron fusion, boron-proton fusion, you need it to be boron 11. And what we can do is we can enrich our starting materials to have isotopically pure boron 11, so we don't waste any energy on B10. We can then change the hydrogen to boron ratio in these molecules. So this B12H12 cluster is a 1-to-1 ratio of boron to hydrogen. We can go to a lower boron to hydrogen ratio or a higher boron to hydrogen ratio, depending on what we synthesize. We can look at the molecular characteristics, such as charge, dipole, symmetry. Do they affect the interaction with laser light? And then lastly, and perhaps most importantly, so far that we've discovered, is the targetry itself. It's not just about the molecule you use, it's about how you fabricate the target. So very quickly, we've played with compressed powder pellets. So imagine now you've got this laser facility. It looks like a spaceship. And in the center of this, incredibly high-tech system where you can evacuate this chamber, which is probably big enough that I could fit inside. And then in the center of that chamber, we've got this, 3 millimeter thick, 10 millimeter tall sample that we're hitting with some of the most powerful lasers in the planet, smacking it to smithereens. And what we've discovered is the actual structure of that target has a huge impact on the resultant efficiency for proton-boron fusion. And it's not all the time as one might expect. So we started off making these compressed powder pellets, really we thought the larger the density, the better the results. And these gave us various interesting pieces of knowledge. We learned how to make these compressed targets better and better. We had also to develop techniques how we could safeguard these targets from exposure to oxygen, for example. We developed what's called the tic-tac method, how we can use very simple things to guard our target material. Here's a picture actually of this is the target here that we were protecting with this tic-tac box filled with argon, and it's the little crane system that we can put it inside there, and once it's been evacuated, we can then use the crane system to remove the protective argon layer. Then another important discovery we realized is this is a picture of the pump laser edge. This is the actual topology of the light that hits the sample, and you can see it's not flat. It's kind of like higgery-diggery and it's all over the place. And we began to understand that to optimize the light-matter interaction, the best thing was to use foam targets. So these are slightly porous targets. I started reading work by this Brazilian chemist who's done lots of work at the freeze-drying of fruits. And I started applying some of his techniques to making our targets. When we began in July 2024, this was how good we could get it, these porous targets. And now we're able to make almost perfectly spherical, ideal targets for this fusion thing. And also we've discovered that we can control the porosity inside the individual targets by adjusting the original concentrations from which we make these freeze-dried targets. And so we can carefully adjust that porous nature. There's a comparison there to typical porous plastics you might well know, such as polyurethane and polystyrene, and the density ranges they have there. So we're getting better and better control of our fabrication techniques, also with the generation of single crystals, some of quite beautiful, perfect symmetries, which give also incredible densities. Lastly, I just include this very last because I was meeting with some people, some interesting work looking at nano objects, metallic objects. I'm working with my colleague Tomáš Baša from our own institute at these nanostructured targets, which are based on colloidal nano gold cores, which are covered by our borane compounds. These, importantly, when they stack up in the crystal, in a crystalline state, they have these interesting voids. These are the gold, the yellow gold pieces and orange pieces. There's a repetitive voids in their structure, and these are really important because we can get electrons to accelerate into these voids, and we can get all sorts of interesting mechanisms for fusion using these nano-structured targets. So this work is now leading to where we are at the moment. So we're putting together now within the framework of a European transition grant, Boron Future Fusion Fuels spin-off. So we've over the last 4 years, the work we've developed in understanding the target tree, we're hopefully translating now into what will be the first Boron Future Fusion Fuels little company. So I apologize for being a few minutes over time, but that's where it ends. I'd like to thank you for the invitation. Hope that I've at least told you something new about boron chemistry and what you can do with it. And if there are any questions, I'll be, of course, very happy to answer them. Thank you.
Thank you for the lecture. And now, if you have any questions. I knew it.
Thanks. So you've shown some figures that were quite obviously from DFT or TD-DFT or quantum chemistry computations.
Yeah.
How exactly were they helpful for your work? How in line are they with your experiments? And were they performed at your institute or somewhere else?
So at our institute, we're able to do ground state calculations, which are useful for structural elucidation, in particular for the generation or the prediction of chemical shifts for NMR spectroscopy, which we can then compare with experimental very easily. But the ones you're referring to, these are excited state quantum chemical calculations, which are far more sophisticated, and we're unable to do that at our institute. And the main people I've been working with are groups from the CSIC in Madrid and also the University of Valencia in Spain. So I've been working with them on, so almost all our publications using those calculations are with the guys from Spain. And they proved to be very useful. In particular to understanding, because so many of these processes are either picosecond or maybe nanosecond processes, therefore they're very difficult to get too much spectroscopic data on, and it's very difficult to fill in the blanks. Whereas the advantage of these computational techniques is essentially you slow down time to zero, and you can then produce this, what's called a potential energy hypersurface, and then that sort of suggests the entirety of the whole transition system. So you can then plot out exactly, how deep is that energy minimum on the excited state, how close is the triplet state expected to be at. So then I can say, I want to promote, for example, intersystem crossing from a singlet to triplet state. Here are the species, here's the three-dimensional XYZ coordinates of the various different potential molecules we can make. Which would you predict would give us the closest singlet to triplet states? And then we can validate that by making all of them and trying, and they are, very, very, they're very good at predicting what these might be. Where might be these optimum crossings, for example. However, the system's not powerful enough. For example, I can't ask the question, okay, so we've got a molecule which has an incredible, almost 100% efficiency of fluorescence, and yet a 10.5% efficiency of laser. We understand why. Tell us what the molecule we should make to shift the laser efficiency up. Then there's no answer. However, if I have some chemical ideas and make a few, it can help me understand why. So then I say, just shoot off the hips, and I make a new compound, and I see efficiency's gone up by 5%. Okay, and here's all the photophysical data we're able to experimentally measure. Then I give it to them, and then they can say to me, aha, we've done it, we've run this, here's the potential energy. We think it's because of this. And that's the big thing.
Any other question? Další otázka? Myslím, že můžeme pokládat otázky česky.
Jo.
Takže se nebojte. Okay, so I would have one. Why is it in anti that it's optically active and laser enabling, and the SYN is not?
Okay, can you throw me one of the... So you can see here, this isomer here is essentially two 10-vertex single clusters which are conjoined by these two boron atoms here and here. Okay, and each of these boron atoms, they're not saturated in terms of their connectivity. And then, so if you then calculate the molecular orbitals, the valence molecular orbitals, then you can see there's a clear delocalization over the two subclusters. In the SYN isomer, which is essentially that 10 unit, not sharing here, but here, then this boron atom becomes saturated in terms of its connectivity. And that disrupts the molecular orbitals from going across both subclusters. So it's to do with that. It's to do with how the two subclusters are fused. If you imagined in terms of, if you imagine something like naphthalene, right, where you've got a sharing of the two carbon atoms between the two subclusters, if that were to be somehow disrupted and one of those two carbon atoms changed its connectivity sphere, then maybe you couldn't get delocalization across both units. Then of course that affects the photophysics.
Další otázka. Wait.
So, as you've mentioned, that boron can produce like a really inefficient laser that has a really high longevity. So, are there like any potential uses for such a laser?
So, well, I mean, it could be used for almost, you could use it for almost every use that we currently have for a blue laser. But the thing is nobody's going to buy it because it gives a third of the efficiency of others. So it's a sort of in essence, you're competing. It's a competitive thing. So if you wanted to buy a laser, whatever the use might be, some lasers might be used for, let's say, the removal of tattoos. Other lasers might be used for, the pumping of experiments for fusion, whatever it might be. Then essentially you're looking at the two conditions of efficiency. So how much energy can you get for each pump? So you excite your gain material, and then how much energy you get out. So it's the ratio of energy in, energy out, and then how long it can survive for. That's the photo, the longevity of these molecules in exciting, emitting. How many cycles can it do before it just breaks apart? So essentially, our compound, although potentially useful for any blue laser application, it won't be chosen because there's better things on the market. So to be able to make this happen, and I've tried now for. Well, I tried for a grant and a half in finding a way to increase the efficiency of the system. If we could make this 4 times as efficient, then we've got something which would be very useful. But we haven't got there yet.
And I assume that the laser that had like a similar longevity curve, has like superior efficiency to the boron laser.
Yes, had about 30% efficiency.
I see. Okay, thank you.
But the quantum yield of 97% is pointing to the possibility that it should be possible, right? To increase.
Yeah. So the 97% quantum yield. So that's the spontaneous emissions. That's when if you're using UV-vis spectrometry, then the pump laser is low intensity, right? So that means that if you can imagine you've got your solution, right, and you pump, then the number of molecules being promoted and falling back down is quite low comparatively to the entirety of the number of things. But in these circumstances, you haven't got a population inversion. You've got a low number of molecules being excited and then going through the cycle. Okay, so at any one point in time, the number of molecules that are excited is low compared to the number of molecules that can absorb the pump energy. If you're with me. If you want to lase, you're pumping with a much greater intensity. So that means that, and because you need to have a population inversion, you need to have at any one point in time more molecules in the excited state than in the ground state. Now, in those conditions, you get stimulated emission, which is the key to lasing. That means that as the molecules in the excited state, as there's so many, that when one of them spontaneously emits light, that emission stimulates the emission of other molecules, okay? But the problem in our case is that because there's so many here, they're also absorbing energy from the pump and they're also self-absorbing energy from the emission. So the laser efficiency goes down. And what happens is they get promoted they absorb in the excited state, pump energy, they take away from that, and then they get promoted to higher excited states, and they get essentially trapped in this cycle in the excited states. And all the time they're absorbing more of the pump energy, and so the efficiency goes down. And I mentioned there's a duality, there's like a paradox about if you remember, the excited state lifetime of this molecule is 11.2 nanoseconds, right? That's long. One advantage of that is it means it's easier to build up a population inversion where there's more excited molecules than non-excited molecules. However, it also means that it's there for a long, long, long time to be able to absorb in the excited state and therefore push the efficiency. So that means if you're just doing a low intensity pump, it's very efficient. As you increase the intensity, the efficiency goes down.
Then would it be possible to use this as a layer to the solar panel?
As a layer to the solar panel?
Yeah.
Well, it's got good solubility in many plastics, in particular polystyrene. We've published some work on thin films with it. So that possibility is there. We haven't investigated it though. Okay. What I did publish was that we can, to try and find a solution about, so in essence, I didn't have time to go into it, but the big problem is the excited state absorption of this compound. Mm-hmm. So the focus in the lab was, can we do a derivative of this compound which will have different excited state absorption properties? It will shift the excited state absorption from frequencies which are not the pump and are not the emission frequencies, if you're with me. And because excited state absorption is just an inherent property. You can't change that molecule itself. You have to make a different compound. So we're making a portfolio of different B18 derivatives, and we got partially there. I could give a talk about that story. It's a really interesting story, actually, maybe next time. It goes in a lot deeper. So today I try to give a wide perspective, but this is like a deep one, understanding the excited states. It's a fascinating story. But yeah, so there's a lot of time we developed to that, and what we did find is that some derivatives, interestingly, would absorb, let's say, this fluoresces at 406, 407 nanometers, and we were making these derivatives that perfectly absorbed at 406 nanometers in the ground state, and then it would then change that energy into about 580 nanometer light. And so what we did is we began to combine this compound with its derivative, and then the effect would be is that these different compounds in a plastic layer would absorb across a wide range of frequencies from UV light, which both molecules would absorb. Then the other molecules would absorb the emission from this, so you'd have a big band of absorption, and the output would be a single wavelength. So it worked like a sort of a funnel of light energy, and that we published, and that's got quite a lot of traction actually. But we didn't take it to the materials to the material extent.
Okay, thank you. Další otázka?
Well, if I'm not mistaken, you've mentioned that Sir Humphrey Davy is your second most favorite chemist. Who's your first one?
So my first one was Alfred Stock, the guy who did the first boron hydride synthesis. Simply because, thanks to him, we have the boron hydrides, but also because he was quite an amazing man. He had to develop lab techniques to handle compounds which were moisture and oxygen sensitive. So, and I should imagine many of your chemistries that you're doing, you're probably using, vacuum lines, etc., which really were developed by people like Alfred Stock because he wanted to make these compounds. And so he was a great innovator in lab technique, he discovered the boranes, and also because at the time they used a lot of mercury, to follow the pressure changes in his new experimental. Then over time, he actually got mercury poisoning. And what I like about him is that once he recognized it as mercury poisoning, he began then to investigate mercury poisoning scientifically, and he began to try to come to a solution to help, get over this particular problem. I admire him for that as well. He sort of decided he was a problem solver. And so that's why he's my number one.
And maybe following like this story, did he get the mercury poisoning from the mercury vapor or from like some kind of mercury organic compound?
Well, that's a good question, because there's I don't know. I'm not an expert in mercury poisoning, but as far as I understand it, mercury itself is not particularly poisonous. It's usually organic derivatives of it. So I don't know completely, but I mean, I presume it must have been from the. I'm not sure whether it was from just the mercury vapors or whether there was anything else going on. I don't know the full story, unfortunately.
Thank you very much.
Hi, thank you for the talk. It was a very nice talk. I have a question that maybe has two parts. It's about the end of your talk, the lyophilization of the particles, the freeze drying of the very homogeneous particles.
Yeah.
So first, very nice progress from the fuzzy particles to the very homogeneous spherical ones. Is it already published, your results on these particles?
No.
Well, so.
I mean, this is quite we're keeping all this essentially under our hat, because this is the basis for this new spin-off company.
Okay, so maybe the second question is already answered. If it can be applied to other materials to form these homogeneous particles, if you think?
That I don't know. Of course, I can't reveal to you any details how we've managed to make that progress. But so I don't know, and I haven't tried. Perhaps what I could offer to you is that if you are interested in doing something like that with your systems, what I could do is I could try it and let you know if it has some success. But I wouldn't be able to reveal to you how we do it.
Thank you. I understand. I'm a theoretician. I was just curious about it.
Right, yes.
I don't have my own systems.
Yeah. No, so no, I don't know. So I'm not sure. I mean, I should imagine it should work for other systems.
Okay, thank you.
Nějaká další otázka? Já bych možná ještě uměl. You've shown that Elon Musk was using the boron for his rockets, and boron seems to be quite an energetic molecule. So why can it be used as a fuel for cars, for instance?
So what happens when the fuels it's an oxidation reaction. So when we take standard hydrocarbon fuels, like what we put into our cars, and we oxidize hydrocarbons, we of course get carbon dioxide and water, and both of which are a gas at the high temperatures of a motor. So they just go out of the exhaust. When you oxidize a boron hydride, you of course get water, but then you get oxides of boron. And these oxides of boron are not a gas. They're like a glassy liquid. And so the effect is you get this wonderful green flame. You release a lot more energy at the beginning, because the energy density in boron hydrides is greater, is superior to that of carbon hydrides. That's why they were looking for that rocket fuel from there. But the problem is that after a very energetic start, what happens is that the engine gets clogged with the products of it, the boron oxides, which sort of form at that temperature like a glassy, syrupy material, and so the engine stalls. And there was a lot. In essence, the secret research was, could they make molecules that had a high boron content and high hydrogen content, but would completely oxidize and form some other byproducts that wouldn't have these, these physical properties. But fortunately, I think fortunately that failed. And so, because I think it's a tremendous shame to take such a beautiful molecule and oxidize it. I mean, it'd be nice to do other stuff with it. Although at the moment I'm sort of smashing it up using light.
Okay.
So maybe I was inspired by the shape of the molecule, but have you tried it for something like drug delivery or other medical applications? Or how's the biocompatibility of these boron molecules?
So as I sort of very briefly mentioned in that time sort of line, that in the application side, there is currently quite a lot of exciting work going on in their use in, potentially into pharmaceuticals and understanding how these things interact with us. Most of the work is done on a compound which is not too dissimilar of this, but if you can imagine breaking this bit off, breaking that bit off, and you join the two with a cobalt, an atom of cobalt, and it's often called cosan. And that cosan, which is that two boron clusters linked with a cobalt atom, that can be that's also in each cluster has got two carbon atoms, and those can be easily derivatized with all sorts of organic chemistry groups, and that enables you then to sort of to do molecular design, to use organic groups which then can target certain parts of the cell or whatever it might be, or indeed certain enzymes or certain other biologically relevant sites. And there's quite a lot of work being published on that, and in particular with it seems to be particularly effective at blocking the activity of HIV protease, and of course, would make it a very effective drug, stopping the spread of HIV in people infected with the virus. And indeed, that work went very close to becoming a suitable, or to invest into proper trials, proper trials to see the actual efficacy of that pharmaceutical product. But that somehow that dropped away, and I think we were discussing this at lunch actually, and I think that's for two main reasons. Firstly is that it's a chemical thing. The problem with some of these compounds, when they get into us, into a water biological system, is that they're not toxic, but what they do is they aggregate, and these aggregates then begin to clog, and it's difficult to get them to where you want them to go. And there is an ongoing research attempt to work out how to overcome this problem. That's why the other main use of these compounds is what's called in BNCT. That's boron neutral capture therapy, which I briefly mentioned as well. That's if you, whereas I'm interested in actually making them be these atoms of boron, because if you don't forget, there's a 80% chance it's a boron 11, 20% chance it's a boron 10. So essentially, on average, I'd expect, three of these atoms to be boron 10 and 15 to be B11. But in terms of nuclear fusion, I want them all to be B11. But in terms of boron neutral capture therapy, you want all of them to be B10. Synthetically, that's a much more difficult thing to do, but you can do it. And these B10 enriched compounds, they can undergo, they absorb a neutron. When they absorb a neutron, then they fragment into a lithium, and it releases energy, and very localized energy, and that's being used to treat various cancer tumors. And there's been some practical use in tumors which are but they have to be on the surface. So I've seen I've seen several talks given by, in particular, doctors from Japan, where they've used BNCT as a therapy for cancer patients where the tumor is located, on the skin or at the periphery, so that they can easily locate the region. So the other thing that comes into it is an economic thing in that its effectiveness for HIV is really that's unfortunately an illness which there's not too much capital to invest into it. The pharmaceutical companies want to have drugs for where rich white people from America suffer from the most. They want things like Alzheimer's and cancer and the rest of it. So it's difficult to find the companies who are willing to put the money, because it costs a lot of money to get something from working in the lab, working pharmaceutically, but to get it into trials where you're testing patients. That's maybe it's $1 billion. It's a massive investment.
Yeah, with the BNCT, I think the clusters are more closed, so I haven't seen anything like that for the BNCT.
Yeah,
That's true. Also, I think something is running in Germany, like clinical test for glioblastoma. That's not my question. My question is about the crystals. What procedure did you use for the needly shape? And you've shown some slow evaporation for the cubes, but for the
that's right.
needle shape, was it like slow diffusion or something like that?
So the needles we can get from sublimation. So if the compound is neutral, so not all compounds, it has to be, of course, a neutral compound like this. So anti-B18, if I make, purify, if I put it into a sublimator, will sublime nicely and form these needle-like crystals. And then if I do slow evaporation, then I can get these really larger crystals. But then different compounds, different ways. Sometimes we do mixed solvent, slow diffusion. So there's different techniques.
Okay. Do I see any further question? I do not. So thank you again.
My pleasure. Thank you very much.
And that's it. That's all.